All right, we are now recording. There we go. All right, so I'm also going to activate the screen share, and that will be screen 1. So everyone can see the old test title.
Affirmative. And your cursor.
Cool. Boop. So we'll scroll through the old test, and then we'll go to these to discuss test concepts. So the thing is, these are all answered. So we know the answers, but we can talk about why the answers are right or wrong, I suppose.
Yeah.
All right, so I was talking with Ryan earlier about these first 10 ones, and essentially if you've taken EE310 or you have like a surface level understanding of semiconductors, you're doing pretty good on these for the most part.
Yeah,
So
could you zoom in a little bit on
I got you.
All right.
All right. Problem 1. So we have true, false. In pure silicon, atoms are held in place by covalent bonds. As you can see, that's true, and that's just what it is. It's not a chemical bond. It has to be covalent since they're all of the same element.
It's
right?
no bullcrap ionic bond.
Yeah, it can't be ionic since they're all the same element. Almost all pure elemental systems are held together by covalent bonds. We have a true, false, except for some slimy ones like chlorine and fluorine. All right. Number 2, true, false. In semiconductors, N doping means an abundance of free negative charges. Correct. N for negative, P for positive. P type has positive charges, aka holes. N type has negative charges, aka electrons. Those are your majority charge carriers. Shouldn't say characters. So yes, this is true for semiconductors. N doping means negative free charges. Number 3, true, false. At room temperature, thermal energy causes some covalent bonds to break, and thusly generating free electrons and holes that become available for current conduction. As you can see, this is true. And there's actually a really nice graph that shows you how temperature affects silicon that is doped and non-doped. So as you increase the temperature in elemental silicon, which is traditionally, or pure silicon, which is traditionally garbage at conducting electricity, you will slowly create more free carriers, that being electrons in elemental silicon. And then what ends up happening is you can actually slowly start to conduct more charge, which is interesting because if you heat up metal, you lose the ability to conduct charge as your resistivity increases. But in semiconductors, heat normally results in an increase of free charges, which is why thermal throttling is a thing. Cool. 4, true, false. This happens to be true here as well. The basic semiconductor construction for a semiconductor diode is a PN junction. This is true. PN junction is the foundation of all of our logical elements, BJTs, MOSFETs. Just the concept of creating, the depletion region in the middle of the PN junction is like, it's the sauce. It's what makes everything chug along.
Kind of a silly question, but is a PN junction going to be identical to an NP? Like, would they ever call it that?
You could simply reverse the order of doped silicons. Actually, fun fact. So in a 310 homework assignment that I had to do last semester, there was a question where they flipped it, but it's simply all that changes. It's the direction of your overall like flow of current, right? Because there's a reason it's positive to negative.
Right.
And it's because of how it would function in a circuit, or more like how it would function when charge is passed across it. So if you flip it,
change which direction the forward bias is.
You reverse your biasing, yeah. Standard, it's PN junction because that's how we do circuits.
Left to right.
Yeah. Okay. So then, number 5, true, false. Intrinsic silicon has no doping. Yes. Intrinsic, aka pure, has no doping.
Extrinsic does have doping.
Yes, extrinsic does not. It is not pure. It will be doped. Number 6, a semiconductor diode has only 2 states, forward biased and reverse biased. Correct. Forward bias allows for minimal voltage loss and current to flow relatively freely. Reverse bias, the diode will freak out until it explodes. Better explanation, the diode will limit current passing on the order of micro to nanoamps. It'll let a little bit of that pass, but most of the other current will be dissipated.
But an ideal diode would just have no current.
Of course. An ideal diode would have nothing leak through, but the real world hates us.
That's right.
Number 7, true, false. A full wave power supply circuit must have more than one diode in order to conduct full 360 degrees of input waveform. I hope we all understand that this is absolutely the case, because we can actually use question 6. If you have an understanding of question 6, you can probably logically figure out why this is the case. So if you have one diode, right, and it's either forward biased or reverse biased, AC energy or AC electricity or current is going to be positive for a change. It's going to increase, peak, decrease, hit 0 point, and then decrease, negative. So it's going to reverse its polarity over and over again. The diode will only pass half of that. It'll only pass, depending on the biasing of your diode, which direction you're facing it, it will only pass above the 0 point or below the 0 point on the AC curve, on that sinusoidal waveform. So if you have a single diode, it's not possible to conduct full 360 degrees. Therefore, this has to be true. A full wave power supply must have more than one diode. If you have one diode, you can't do it. Therefore, this question has to be true. All you need to know is how diodes work with regards to forward and reverse biasing here.
To call it a full wave power supply, is it just implied it's a rectifier?
Yes. And a full wave bridge rectifier, right? That's the full name of the rectifier that we would have to use for this.
Right.
Yeah. So
Which
yeah, it's
this is
implied.
about smoothing it out when it comes with the bridge part.
Gotta make it hot. None of those little, dips, all of us hate little dips in our nice, current lines. We want that to look like it's coming from a 9-volt battery. Shouldn't have said that 9 volts suck. All right. Number 8. A Zener diode must be forward biased in order to perform the Zener task. This is absolutely false. The Zener diode operates in reverse bias. That is how it is designed to function. It's just what it is. And we can hop over to the Zener diode PDF and let's see if they talk about it anywhere, shall we?
I think it said at the beginning.
Yeah, we'll go back up.
Operate in breakdown or reverse bias.
Yeah, breakdown is another word for
Oh, and
reverse
it
bias.
actually, the schematic symbol kind of looks
backwards.
like a dude dancing. So he's breaking it down.
Okay, I don't want to hear it. Yeah, but yeah.
Ban someone.
Honestly, that fits. How do we ban someone from a Zoom call? Yeah, so we were just an 8. So yeah, so the Zener diode must be reverse biased in order to perform the task. It has to be operating in breakdown. So this is a false answer. And then we have the depletion region for a PN junction has no free charges available for conduction. This is true. In 310, the way I actually have lectures or study sessions from 310 on the same channel I post these study sessions on if you ever want to go get a refresher. But the depletion region for the PN junction, I always explained it like this. If you have free carriers on one side that are positive, and then you have free carriers on the other side that are negative. Damn, I don't remember how I explained this that well. Let me think. So it's, what was it? Positive, negative. Oh, it's because of the biasing. That's how I talked about it. It's because of the biasing. So if you put a positive on this side and a negative on this side, the diode won't operate because it'll pull. Yeah, sorry. Okay. I'm going to draw this here so you guys actually can see what I'm doing first off. How do I use Zoom to draw? Over here. There we go. Draw. There we go. So if we have lower that DPI, do you guys see the DPI thing in the corner?
Yeah.
That's funny. All right. So let's say we have a positive charge and a negative charge. Here's your P-type section. Here's your N-type section, right? Now we're going to apply an external voltage onto the system. Now, applying external voltage, as you said, you tie your positive to over here and you tie your negative over here. Your high voltage, low voltage. What happens? Electrostatically, this repels. These systems come closer together, and then they can allow charge to conduct. It closes up that depletion region and allows stuff to flow. What happens if you do this the other way? You apply it in reverse bias. You put a negative here and a positive here. These pull away from each other, thereby increasing the depletion region, which results in no charge flow because the region has increased and the resistance of that area is far higher. So that's just electrostatically how I think of how it operates. If I just hit X, does it disappear? Clear. Nuts. That's awesome. All right. So the depletion region has no free charges available. This is just something you memorize. There aren't free charges available. Otherwise, there'd be leakage current. I say that, but if you take 310, you find out that there is leakage current, but it's for different reasons, like diffusion and stuff. 10. A hole in our semiconductor context is a space where an electron was that has mass and electric charge. This sounds like some weird quantum stuff, and it kind of is, but it's true. A hole is just the positive result of an electron's absence. So if you have a neutral system and you take an electron away, it becomes a positive system, right? Because you lost a net negative charge. So your net neutral becomes positive. And that's essentially what this is describing to you. Electrostatically, or just physically, if you take away a negative charge from a system that was neutral, then you've created a positive system. And that's what the hole represents. Don't know about the mass electric charge thing. That's not my job. And then we start with this stuff. Problem 3, given the shunt regulator below, the Zener diode has VZ 10 volts and IZ 5 milliamps. RL is 100 ohms. Find a value for R. So this is just using, from what I can see, very basic concepts to solve for the resistance of something, which is just the load resistor. Wait, no, this resistor. Does anyone have any specific questions? We're going to scroll through these, and if there's any questions and concept stuff that we need cleared up, we'll hop through these to look for answers and discuss it. But I guess we can look at these first. Just think. So are there any major questions regarding this? I know I myself am not a super expert at this yet, but I also don't feel like this is too difficult.
I have a statement about when I did. Now, then again, I was doing it late at night, so my brain wasn't very going good.
Easy.
But my main thing was trying to have. I was having brain fart with the voltage over RL.
Yeah.
And it's just the same thing of whatever the voltage over VZ is given. That's what you do.
So you're saying like
whatever is going over the resistor is what's going through the diode if the diode voltage is given. So
yeah. Well, yeah, in this system, I can definitely see that because they're in parallel, right?
Yeah.
Yeah. So yeah, makes sense. So yeah. And here they just did current sum, found something, and then used that something that they found to calculate R, and they're done. Easy peasy. So this stuff gives me 315 vibes with special sauce that they throw in. Well, I said 315, what the hell? That's this class. I meant 213. There we go. Like stuff that's like, if this were just another resistor, this would not be hard for us to do. But just because it's a funny looking component, it like scares us a bit. But in reality, it has very defined rules, and it's not that difficult to comprehend once you have, like, if you read this, you'll probably be set.
After you absorb all the information, you have a little bit of sensory overload. It's like, oh, that's easy.
Yeah, just sponge that in there.
It's the resistor that works in one position.
Yeah. So now we get to do transformers, my favorite topic, because I'll always remember transformers because I had to hurriedly calculate the current that went across my heart when I accidentally electrocuted myself while backvolting a transformer.
Oh.
That was fun. Don't mess with microwave transformers, kids.
No.
Yeah, number one, actually straight. Here's a fun fact. Microwave transformers are the #1 killer of electronics hobbyists.
Oh boy.
For obvious reasons, most electronics hobbyists don't deal with anything that could kill them. So skewed results, but results nonetheless. So we have
The fact that you call it results makes me uncomfortable.
Hey man, don't question my use of phrase. All right. Given the power transformer circuit below, given the resistor on the secondary output side is 100 ohms with a voltage across to 40 volts, what is the transformer turn ratio? So isn't this just the current relation? No,
Yeah.
They didn't even need to do that. It looks like he just
turn
used,
ratio in the
Yeah.
You just use the formula he gave. It's very...
Yeah, so ratio of the voltages here, it looks like.
The only one that I did not know going into this was the resistance seen by the priming wire. Or winding, sorry. It's technically wiring. But like that concept, it makes sense after you look at it, but it was just one of those things I don't remember him talking about in lecture.
I think it is, he just gives the equations for it on those lecture notes, but I don't think he really like talked about it. But he does skim through a lot of stuff, so.
And then talk about drinking moonshine in a...
Dude, he's got some great stories.
I would love to have him as a boss.
He's got excellent stories. I mean, I'll never forget the method for controlling op amps because he called it like the chip in a horse's mouth or whatever.
I can't remember what it is.
I don't know what that specific thing is called because I'm unfortunately not a Texan rancher.
My dad used to be on a farm in
It's a bit. That's what it's called.
Yeah, there we go.
Makes sense. Yeah. So here, a lot of these equations are pretty. Rip, Ryan lost. We lost out on our boy Ryan. He was in the car, so his connection dropped. Oh wellsies. So that's actually fun. So if you ever want to have fun, have like a transformer that's got a turn ratio of like 200 or something, like a disgusting ratio. And then the one with more windings, like the secondary traditionally for like a microwave transformer, I think, put the voltage on that side and get the disgusting current out the other, and you'll see what happens. You can probably see a bunch of YouTube videos where people do that exact thing and like melt metal with it. Yeah, don't touch it. It also makes a really big humming sound and it's annoying. All right, so here we have 4A, which is asking for the resistor, which is just, no. 4A is asking for the turn ratio. And here's the B, which is what's the resistance seen by the primary winding, which is what you mentioned, which is, this right here. And this is what? This is just impedance.
Yeah.
Which
yeah.
here it just happens to be a resistor, but in theory he could be like, oh, have an inductor or something, or a capacitor, but I doubt he will.
You never know.
But he could, so don't forget it.
Okay, is it me, or was the test like the next like a good bit harder than all the practice stuff that he gave out?
I kind of agree with it to a point. If you grinded on those homeworks, some of them were a little what the hell, but
yeah, the homework was, in my opinion, it kind of fluctuated between being really hard and being like, oh, that's easy.
Yeah.
And the test was kind of in between that.
Yeah,
I think the hardest thing about the test for me was just like with the design problems.
Coming up with a circuit on the fly.
And it was that thing of like both my circuits were like, I was like, I'm pretty sure these are correct, but like it's almost too open-ended in a sense.
Yeah. I actually, ironically, got full marks on the design problems, which I thought I was going to get wrecked on, and I lost points for stupid mistakes on the problems I thought I had down pat.
On the first one, my final answer, I had 1 decimal point off, and that was 2 points.
Yeah,
ouch.
Ironically, the design problems were the things that I knew most on the test.
Because I know
everything else I was pretty bad at.
The design problem for the integrator.
Yeah, you just add a capacitor on top.
You literally just did the one that everyone was having issues with on the practice test.
But that one was on. Yeah, that one was. It was more or less the same as the question on the practice test, and then the one with the
polynomial implementation.
Yeah, I did a weighted summer for that.
Yeah, same.
Basically, straight up the example weighted summer, like in that section of the textbook.
You just change the resistance values.
Yeah, pretty much. So.
Yeah. So now we have, what is it? We just did the resistance scene, which is just a relatively simple, impedance calculation involving turns and impedance on both sides. Then we have 4C, which is what is the primary current. And yet again, everything with regards to transformers is basically just figure out what your turn ratio is. And from there, it's pretty easy to chug along. So shouldn't be too big a whoop.
Yeah, it looks like this is just like, it's basically the 3 different applications of these like ideal transformer ratios.
Yeah. And then D is what's the secondary current, which yet again is just what it is. Pretty basic thing. And then we have the basic overall equation, which can essentially be rearranged to do most of this, if not all of it.
And I emailed him last week about a equation sheet for this exam, and he said he was going to put it on Canvas.
Yeah, I haven't. He hasn't put it on yet, but if he does put it on, as you say, that'll be great.
Yeah. He said it would be. This was he emailed me back yesterday and said it should be tomorrow.
Yeah.
I've had classes where they don't let you have one of those, so I just memorize it in my head.
Yeah, I always have it memorized in case.
Oh, for sure.
Hate the second you get the test paper.
Yeah. In 310, we were allowed to make our own equation sheets, and you bet I put everything on that.
Oh,
I had that for Physics 1 class that I took at a private college here, and this kid literally had graph paper and wrote every single thing. I swear he wrote the whole chapter on his book, on his piece of paper. It was disgustingly small font.
That's a legend. I had a kid who did that, but he also brought a magnifying glass with him.
There you go.
Legend. All right, now we're on number 5, which is give the circuit below using an ideal diode model assumption, which is all of this.
Now, if these were questions on the test, would the drawing come with it?
Unfortunately, no. You need to understand through a question. Wait,
Right.
actually,
So
I
it
don't
just
know.
seems
Maybe
weird
they
that it's like
I think it's one of those things. If I think it would.
actually, yeah, because here it says using the ideal diode mode assumption, compute ID the diode current. So
It says given the circuit below.
Yeah.
yeah, so
it's
we are
just so
given.
weird because I
Yeah,
can't tell what's given and what he's using his
yeah.
work.
In this one, obviously, he'd have to give us the circuit because that's where our values come from.
But
Yeah,
what
I
about the
was-
last one? The power
Given
transfer.
power transfer. Yeah, okay. So it looks
Yeah,
like
well, he
all,
like with
right
the
up
power transformer, he tells you all the information on it.
given the
But he
shot.
didn't
Yeah,
tell us what
every
the input was.
120
Like
volt.
I think
60
that
hertz
transformer,
sinusoidal
other than
supply.
the power source, I think we could make that on our own.
Right, but
This-
without
this
the power source, you couldn't calculate the ratio,
Exactly.
right?
Exactly.
So
No,
the
he'll give
drawing
us.
has to
He'll
tell
give
me.
us this.
So
He'll
you
give us this. We do have a power source
Yeah,
here
he
though.
would have to.
But yeah, he'll give us. Oh, and then he has a secondary voltage over here. He tells you what the secondary potential is.
Well, that part's in A. It says the voltage across the resistor is 40.
Oh yeah, so maybe he just drew it on.
He just never told you in the preamble what the
this is.
voltage on the
Yeah,
input
but
was.
he's in number 4. Now that I read back, it says given the power transformer. So in all of these questions, including the first one, he gives the circuit.
Yeah.
So
Yeah, and I mean,
Okay.
we should assume that he'll give us enough information to answer
yeah,
it.
and for the op amp questions on the last exam and the
Mm.
practice test, he gave the circuits. So
Yeah.
I think that'll be consistent.
And I mean, and these ones, you know, there's not a lot of. It's really this is mostly, you know, intro to semiconductor concepts and transformers, and then a little bit of understanding about how to use the one of the more fundamental semiconductor arrangements, the diode, and what it's useful for. Unlike op amps, diodes do not haven't dropped away with time or become irrelevant. Diodes are still nuts, and they're used everywhere, and I hate them.
So did he give right there the assumptions there to the right that are handwritten?
Assume D1 is always, what does he say there?
Forward bias.
Forward
and
bias.
then-
Okay. Yeah, you're right. Forward bias.
And also he flip flops between having voltage drops of diodes being 0.6 and 0.7. It
And
kind
I
of-
was gonna say, in that V. sub
okay, yeah.
T-
First, so here's something with regards to that. In 310, you learn the voltage drop's supposed to be like 0.7, so just stick with it. Stick with
Yeah.
0.7. That's a good one to stick with.
Although, if this is a multiple choice test on Canvas.
Oh yeah, I forgot he said that it's
might
multiple
be.
choice.
Oh.
Then I would calculate like what I'm planning on doing is doing like 0.7 if he doesn't like specify one, and then if that math doesn't check out, I'll do
Do
0.6,
0.6.
assuming my math was right.
Wait, 0.66 is what he's been saying?
No, 0.6.
Okay.
Like basically saying if
That sounds
multiple choice-
suspiciously like a germanium diode voltage drop.
I think it's less than that, isn't it?
I
No,
don't remember.
It's like 0.3.
Yeah.
Yeah, I don't remember.
Also, V sub T here, he gives us 26, and the textbook gives it as like 25. So. pay
Oh,
attention
hey,
to that
real
as
quick, have
well.
you guys? There's this YouTube channel called like the Organic Chemistry Tutor, and he
Oh,
has
you
a
bet.
bunch of stuff on this.
I mean, I know of the chemistry store. I haven't looked at his content with regards to this, but
It's actually pretty good. Every once in a while, there's like, I don't like that, but
might give it a peek. All
yeah.
right, so
Yeah.
what is this one?
Anyway,
Ideal diode model assumption, compute ID diode current. So ID here looks like it ends up being the voltage divided by the resistor. Are you kidding?
Yeah, I guess he's just doing
it's literally like the easiest problem ever.
This is
Yeah, it's like-
if I get jumped and he gives me like quantum physics problems, I'm gonna be somewhat disappointed.
If he gives us the same type of level test as this, I swear some of us could finish it in less than 20 minutes.
Yeah, I agree with that. I agree with that.
And that's why I'm a little suspicious.
Yeah, it's a little sus, but
Yeah.
we'll see. So now let's get to B, which is using
Although, I mean,
constant
think
voltage.
about
Oh, yeah.
there was basically that problem on the first test where you just had to like list the ideal op amp assumptions.
I mean,
Oh,
there
yeah.
was also a problem on the first test that was identical to a homework. It was a homework problem.
Yeah.
Was it
Like-
number 4, the op amp?
It was an op amp. I think it was like I think it was number 4 or number 2. It was one of them. It was just like
I'm looking at it.
identical.
And didn't
I
he
have. Oh yeah,
say-
it was number 2. Number 2.
It was
they
literally
were-
just
number
sharing.
2 and 3 were almost exactly the same.
Yeah.
And didn't he say he pulled the Thevenin equivalent circuit problem from the textbook? I think he said that in
Yeah,
class
probably.
last week.
Either way, yeah. So
Yeah, the Thevenin equivalent was not too bad.
So anyway, for this one with the ideal diode, we're just assuming it's just a wire, right?
basically yes, because here's the thing. The thing with part A, looking at the circuit, that is a linear voltage source. Like that's a battery for our purposes,
Yeah.
right? If you put a diode in series with a battery, it may as well be a wire, right?
Right.
Like if we're assuming that thing's ideal, there's no voltage drop in the diode, there's no problems. I mean, it's a wire. It's what it is.
Yeah.
And it's a DC voltage source. Like,
Yeah, like if this was AC, this would be a different story.
They're just trying to run up the production costs.
Basically, yeah. I mean, I'm gonna be real with you. I've literally I've ripped a lot of things apart in my life, and I have seen diodes that are in circuits that have like linear
maybe
sources.
there's something else part of the circuit we don't see, and they're protecting the battery.
That's also a possibility. You could be protecting like let's say you have a kid's like remote control car. If they spin the motor's wheels, that's gonna generate some current in the motor. And
Perhaps,
if you
and
have
you don't want to
diodes,
back current the
Yeah.
battery or something.
so I can understand it, but I've seen some really stupid diode purposes. Sometimes they just do it because they can. All right, and let's, B is using constant voltage drop model for the diode compute ID. What do you know? He uses 0.7 here, which is probably the reason one of you mentioned earlier.
Mm-hmm.
But yeah, so we lose a voltage of 0.7 across this. So then now that we know that, that means, oh boy, we lost 0.7 volts. So now we only have 9.3 volts. So calculating current here is still, child's play. Because it's in series with a resistor. So whatever the current for the circuit is the current for the... What's funny here is we could technically calculate the air quotes resistance of the diode here.
Oh boy.
But there's no reason to. We just assume a constant voltage drop and say that's the day. So that's that. I don't think there's any confusion with regards to this. This might as well not even have had a diode in it.
Is the voltage drop on a semiconductor due to resistance?
Okay, it's because
kind of.
okay, it requires like a startup voltage.
Oh yeah, there's a
Right.
voltage you have to get to.
It's kind of like
Oh, does it turn into heat?
no,
No.
I don't know. Like everything does turn to heat eventually. But it's not like primarily heat. It's just kind of think of it like, you have to get over that p-n junction type thing. So you have to get a certain amount of potential buildup to cross the junction.
So
Basically, because a junction's kind of like not super charged in the middle, kind of have to get a little bit.
It doesn't got anything in the middle. So think of it. So remember that electrostatic model with the positive charges and the negative charges that my weird approximation thing. I'll draw it again, and I can kind of have another explanation version for why this is. So you have your P, you have your N, and now let's put something across. Your positive charge here. So this is your your source voltage here, and this is your sink, right? Here's your P and here's your N. Now, yes, these are pushing together, and this will close the depletion region by forcing those charges together, allowing stuff to flow. But here's your problem. You need a certain strength of electric field to force this shut.
Right.
So once you reach that strength, charge immediately flows. So the current, like your voltage to current here, you'll
It's
be like
only
boop,
whatever's
boop,
above that activation.
yeah, it'll be like
flow.
boop, 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 boop. It'll go to 0.7, and then it'll just go.
Yeah.
It'll
That's
just
where
go
they
to
were
whatever.
Approximating it with like different they had piecewise functions, they had
Yeah.
exponential functions.
Yeah,
That's
it'll go to whatever your load is at that moment. So that's what the 0.7 is for. Now, I guess for some reason, approaching that 0.7 results in a net loss of that energy to get it there to start, and then the rest can flow relatively freely. So there's some mechanic that results in that energy leaving system.
And it most likely turns into heat or some other.
Yeah, something happens to it.
Okay, so then also with the PN, now does P have the holes in it?
Yes. When you
Okay.
dope something positively, it means that you have generated excess holes, meaning
So the
you've
P-
added elements that steal free electrons from the system.
The P side has fewer electrons, and so you turn it on by adding more electrons, is that correct?
So the P side has majority carriers of holes. So
lacks
it's not as
electrons.
much as turning it on per se, because the electrons they're charge carriers, because they flow. So technically they don't leave per se, they simply move slight position. Yeah, it's just weird. So when you put your load across the system, you have your holes here, and the electrons enter the system and can fill those and use the holes to travel.
But
And
now, are you
here-
saying that electrons are coming from the positive terminal?
Functionally, if I remember correctly, Ben Franklin was wrong, and that's not what happens, and it goes
That
the
is,
other way.
it's not, yeah.
But conventional current is how we think of it. I'm not
The
qualified
answer
enough.
is yes, but actually no.
I'm not. I
So,
don't have enough
But
info.
I'm just trying to like think of your diagram. We're
Yeah.
moving current left to right. So that means that there is an abundance of electrons coming from the left, moving towards the right.
Abundance of charge carriers. It's all about charge carrier motion, because holes can carry charge the same way an electron can, which is weird because it's
Okay.
technically an absence of an electron, and that's it. But it's so the charge flows across your system, given our conventional current model that we use, and it uses the holes and the electrons to move. So once it bridges that gap, they simply are allowed to flow across. I should have paid more attention in 310. Yeah, so that's as much as I can say on that right now, unfortunately.
Alright.
I know for a fact, if you really want to know the answer to that, we actually had to answer stuff like that for 310 exams and quizzes and homeworks and such. So on the same channel I post this, I mentioned earlier, I have review sessions for all of 310. So if you circle through like the first review session for 310, that's like relatively an elementary topic at the beginning. So that's where that would show up if you wanted to know for sure Z's. Or you can wait to take 310. That's also allowed.
All right.
I don't recommend it.
I don't have to take
I
that.
mean, oh, you do? Are you CPE?
I am CPE.
Get out of here.
I will gladly.
Leave.
No. He's a viable
Also-
member of society.
Hey, just FYI, his notes for like all this stuff that's review from 310 are not handwritten.
Yes.
They're like actual lecture slides, so they are much more legible than some notes are.
Wait, this is the wrong. I did this wrong. And I opened a calendar. Useful. Okay.
Yes, you have Among Us and Minecraft.
I was looking at that too.
Beautiful.
This.
Too intellectual.
I think it's this.
All you really need.
Wait, this is just MOSFETs.
No, it's on Canvas. It's called Lecture 7 and 8, Part 1, Semiconductor Diode.
Boy, your inbox hurts me.
I'm never gonna look at it either.
It hurts me so much as oxygen before. Holy crap.
Don't question it. There we
I'm
go.
not, I'm just scared.
Here we are. The PN junction. That's the elements required for doping. So here's something. Here's a picture that might be able to use. Here's your p-type. We have mobile positive charges and bound negatives. There are still electrons in the system, but here we can talk about it going up here. So here's your doping. Here's your p-type. Boron. Anyone remember where boron is in the periodic table?
Like,
Number 3.
Hydrogen, helium, and well, lithium is number 3, but it might be in the third rank or whatever.
it's
It
like
means four.
it's like towards it, right? I'll just look it up.
Hydrogen and helium and lithium, beryllium, boron is number 5. So number
Oh, that's
5,
okay.
right? What are
That's-
the
I confirm.
anyone remember chemistry? How many electrons are in boron's outer shell?
I
Three.
believe 3.
That's what I was
Uh-oh,
thinking of.
3. That's a
Here's
dangerous
3.
number. Silicon has
scary.
4. If you put boron into silicon, that means the crystalline structure is lacking an electron for covalent bonds to form. Uh-oh, that means you create a net positive charge that flows around every time, a shock to the system happens. Any type of change in the environment causes these holes to randomly, spontaneously vibrate around and just vibe. So that's what that happens. Then fundamentally your N-type, how's that going to happen? You're going to have 5 valence, I believe, right? 5 valence electrons.
Got an actual one.
So we have arsenic. Phosphorus is a common one for N-type. So phosphorus
Phosphorus is
has 5. Phosphorus has 5 valence. So it's based on valence electrons. So we have excess electrons and excess of holes. So an excess of holes is actually an absence of electron, and an excess of electron is an excess of electron. So it's weird. It's all
And
about the
absence
electron.
of holes, which
Okay.
are absences of electrons, which
Yeah, so you just say more electrons. So everything
Yeah.
is with regards to electrons. So here's what that looks like fundamentally down here. And this is describing the normal structure of intrinsic silicon. And then when we get to extrinsic, we would actually lose one of these, and losing one of
Uh-huh.
these generates, your hole in the middle instead. And like, if your environment's messing around, there's not a super large amount of stability into that system. So it could be more temperature, it could be anything, and that could cause this hole to be like, oh, I want to go here now, and now I'm here, and now I'm there. And then
Sure.
electrons will reclose those positions. So it acts like gates that just push the holes through, and it allows the holes to transfer charge because it's all about potential difference. Here's your hole. Here's your broken. So there's your hole. You're missing something. And then, yeah, and here's your extra electron over here, which is problematic. So this one would just, yeah, here's your extra electron star here. Let's see if there's anything more. That's for holes. And here's the junction. Diffusion. Oh boy, let's zoom in on this. This is an important figure. Can I not move this effectively? Here we are. Oh yeah, you see these?
There's a depletion. That's what I was talking about.
Yeah, you see
I
these
was like, pushing
figures?
it off.
You see that VB? Oh, you're gonna love that. So here's your P-type and here's your N-type. They're not touching. Then you touch them. Remember, P-type has holes, right? So fundamentally, this is positive, this is negative. So what's gonna happen? You touch these together. But here's what's important to remember. Holes are free positive carrier, and electrons are electrons. They are a free negative carrier. N-type has free electrons, P-type has free holes. What happens if you touch a limited portion of a system together that has on one side a net charge of -1 and on the other side a net charge of +1, net charge of 0 in the region? This depletion layer fundamentally is intrinsic silicon again.
Just think of it as like the demilitarized zone.
Yes, fundamentally, your holes from this side and your electrons from this side have touched and come into contact. So the electrons come into contact with the holes or vice versa, and they neutralize. They fill the spot. Now they're happy. But the problem there is intrinsic silicon sucks. It's complete garbage. Useless. Nothing can get through. I lie. It just has a high resistance. It loses a lot, right? So what happens when you add your big positive charge, you add your positive negative, and you bias current across here, is electrostatically, this is a fixed amount of wipe. But when you move this together and keep pushing it, and you have a net excess charge flowing across, it breaks this equilibrium in the middle. Because if you were to only touch the P-type and N-type of the silicon and have no excess biasing on the system together, such that both were completely in contact with each other everywhere, it would just become intrinsic again. Fundamentally, it would neutralize and become intrinsic. But the second you put an excess charge across, it breaks this equilibrium and allows charge to flow normally again. And that's how the PN junction operates.
So by adding
an excess bias, an external bias on this stable system, if you leave this how it is, it stays depleted and charge will never flow.
Right. No, that makes sense. But if I add electrons to the P-type side, what happens?
So you add electrons to the P-type side. It's not as you're adding electrons necessarily. It's more that you are having a positive, what is it? It's more that you're having a bias across the system. So it could also be
like
holes.
A potential voltage difference.
Yeah, a potential voltage system will cause the depletion to shrink up.
But that's caused by.
It's caused by an electrostatic effect. Now, I don't know if it's just electrons that do that. That's the thing.
Well, you could have an increase of electrons or an increase of positive charges,
holes,
but
or
essentially it would be like the same thing.
That's the thing. Because what happens is the whole reason that what happens here is your depletion layer decreases. So what that means is this equilibrium that used to be equal means you're breaking it. You're adding a hole back here, a hole back here. This isn't intrinsic anymore. You're adding an electron here, an electron here. And what that does is the depletion layer becomes shorter because you've essentially returned, the charge disparity back to the system on each side. Now the depletion layer, I don't think ever drops to 0. Like I think it's always there, but the resistance of that intrinsic silicon drops to a point where eventually it's fundamentally not there and you don't need to care anymore. And that's how it is. So that's the same reason like this junction still dissipates energy in the form of heat because of this resistance, which is higher, like disgustingly higher than this or this. Dope silicon's really good. So it's just about introducing those charges back to the system to take it from this fundamentally intrinsic representation and putting it back to its extrinsic doped variety to allow charge to flow. And that's all due to the external biasing. Is that good enough?
It helps.
Hell yeah, believe me. Nope. All right, let's go back to where we belong. That's enough 310. Here we are. So we did this already, or discussed
Next
this.
one's gonna be rough.
All right, 6.
I hope we don't actually have to plot this because
I saw in his study guide, he said know this, like tattoo it on your body is what he'd say. So definitely gonna have to do it.
Oh.
Given the below is the operating characteristic for a non-ideal semiconductor diode, D1. Given the circuit that the diode is in and a Q point as marked, what is the resistor value given the value of 3.5 volts DC? So A. He did A next? Wild. So here's our Q point, right?
All right, now this is what I'm asking real quick. Are we going to need to plot this chart exactly like this?
I'm not sure. Wait,
Like,
no, he says given below is the operating characteristic. With the Q point is marked.
That
so
was what I was scared about. Was
he
graph this piece of crap. Like,
yeah, he would give us the graph.
You have to plot the load line, which is the
okay. Yeah, the load line. That load line's not too bad.
Yeah.
Yeah, plot load line. Yeah. Okay.
All right, that makes more sense.
I'm assuming we were probably just given the like exponential curve.
It says Q point too.
And the Q point, right.
So you'll be given your exponential curve and your Q point.
And that's where you know.
Wait, isn't this? Didn't I just draw this? Fundamentally, like the startup voltage.
In a way,
yeah, very similar.
Part, but I didn't do the load line.
I didn't draw the load line. Yeah.
Yeah, and then the Q point is where the load line should intersect with the exponential, and that's like your quote operating point for your diode.
Nuts. All right, cool. So let's go down here. So we have a VD, which is right here. Well, so this is from the Q point. So we pull VD and ID from our Q point. So that's where we get this information from. We do some KVL derivation, which looks like this, I suppose, which for this, I assume this is given as well. If not, I'd be disappointed, but it looks like every single circuit we've worked with thus far with a diode is a DC power source, a resistor, and a diode, so shouldn't be too concerned. So we derive this KVL from this circuit using this little thingy. And this is for, he's pointing to B here, but let's look over for this resistor. So using that KVL, we have the resistance of this system is going to be equal to V minus VD. V given as 3.5 previous, VD given as 1.45 from our Q point data. ID given as 3 milliamps from our Q point data once more. Do this computation and boom, you have a resistance value that I would hate to have to make in real life. Then we have B, which is our load line, which is, looks like just this equation, which as it says here is derived from KVL. So ID once more given from our Q point data, 1 over R. So I understand why, don't know why he calculated this first. No, he just gave the load line equation. He didn't graph it yet, but you need this resistance value, which is why it's ABC and not BAC, but it doesn't really matter here. So you have 1 over R times the once more voltage from our Q point plus V over R voltage from the circuit 3.5 over R. So it's the same resistance. So fundamentally,
we're more used to it looking like V minus VD divided by R.
Yeah, and that's the exact same thing.
Yeah, just,
Yeah, rearrange that equation. Nice looking. We did already, and then from load line. So what is C even asking? C is asking plot the load line. Oh, B and C are both for load lines. What is C asking specifically? From load line, what? Plot the load. Oh, so this is just him finding intercepts, isn't it?
Yeah.
Okay, cool. I hope all of us understand algebra, so we're gonna skip that. I'm not actually gonna skip that. So, even though it is just algebra, it's still probably best so we understand what's happening. So you need your 0 points, so your 0 on your y, 0 on your x-axis, and then you use them from this load line equation you derived from KVL previous. Fundamentally, this equation will be the same across the board, assuming you can simplify your resistance down to just one resistor value, right? Otherwise, it's going to look a little different based on your resistance / impedance of your system. Although there shouldn't be impedance in this because it's DC, but if there were, that'd be unfortunate. Now we're on 7, but this was 7, but oh well. 7A, compute the value of thermal voltage VT for a semiconductor. This is just 310, bro. What the hell? Okay. Actually, now I actually recommend that people go watch my review sessions on 310. We actually, like, this is a problem we would do on the test in 310 straight up. Or I wouldn't say this is the whole problem, but this is definitely a component. Thermal voltage is important. Compute the value of thermal voltage for a semiconductor at 60 degrees Celsius. So first off, we need that in Kelvin, which is exactly what he did. He computed it to 333 for 60 degrees Celsius. What is that, kappa? Is that what that thing is? Kappa T? I don't
Yeah,
remember.
which is like the Planck's constant or something.
Yeah, so
like
he
that.
has that as 1.38
Yeah,
times 10 to the
Boltzmann's
negative 23.
constant.
Yeah, and then
Yeah, not Planck's.
under that, he has Q. That's the charge of the electron. That's a bad looking Q, but a Q nonetheless.
What does he give down below right there? Does he give Boltzmann's and
Here's your electric charge, aka electron.
Okay.
He gives
So-
Boltzmann,
so
and he
part
gives
A-
the Kelvin degrees Kelvin computation for
So
Celsius.
part A, you literally just need to know the equation.
Yeah, which is VT is equal to
Yeah.
kappa T over Q. Then next it asks, using exponential equation for a non-ideal semiconductor diode, what is the reverse saturation current IS, assuming forward bias, with the diode current of 1 milliamp and 0.5 volts across it? So yet again, this is yet another equation. ID is the given here. It's 1 milliamp. And VD is 0.5 volts given. VT is calculated previously, 28.72 millivolts. So this is just an equation. I mean, it's not even a difficult one, honestly. It is what it is.
And he omitted the -1 because that number is stupidly big. Or
Which
actually,
one?
is it small? Well, right at ID.
Negative numbers approximate to 0 when they're exponentiated with E. So you can just exclude them if they're part of a
the
sum.
-1 usually. Oh, okay. I see where you're getting at now.
Yeah, so it gets tiny. No, in 310 we use the exponential equations and E is everywhere essentially, and there's a lot of questions where you just get to drop half of it out almost immediately.
Yeah, and I think the textbook gives the exponential equation without the -1 as well.
Yeah, because it's basically pointless.
Right.
For our purposes. Because here's the problem. Look at how small the saturation current is.
Yeah, that's
like you'll find. And then here's the thing in C, what is the current through the diode ID when the voltage across is 0.7 volts? So boom, we've reached that magic number. So we go through and we use the equation. So here we have what is that, a VD of 0.7 now. We have our VT from previous calculations, and we have the IS previous. So this time he simply rearranged the equation for ID and is asking for ID, as opposed to part B where he gave ID and asked for IS. But we still use IS because actually here's an interesting concept here. So we calculate IS. So if I remember correctly, in 310, you're given IS as a constant most of the time. Like you don't compute it, it's just there. Like saturation current just is. And here he had us compute it as an exercise, I suppose. It's good to know how to do it. But most of the time, what you want to know is you want to know the current through the diode.
Mm-hmm.
So why do you think he arbitrarily gave us 1 milliamp and 0.5 volts? What about the data points given there for part B is important for IS? Like why is that a valid computation for IS with those values? The answer is because 0.5 volts isn't enough to start up the diode into conducting phase.
Okay.
Because here, look, in C, all he gives you is that it's 0.7 volts. And that's right there, and you get to start transmitting. Because look, IS is almost picoamps. That's nothing. That isn't conducting shit. That's doing nothing, right? So fundamentally, he just gives us some current value that's acceptable and 0.5 volts. This could have just as easily been like, 0.1 milliamps and 0.2 volts. All it needs to be is give data points that can compute IS to some disgustingly tiny amount of current. Because what ends up happening is look what happens with that E value, right? E is no longer in the denominator. It is now part of the numerator. E is a disgusting number because E to any large positive number is ridiculous. So you need to have a comparatively small IS to make your current across your diode remotely acceptable in real world terms. So mathematically, that's a good way to think of it. But also fundamentally, it's interesting because in 310, taking it beforehand, you'd see a question like this and be like, why are they asking us to calculate IS? It's just a constant. But it makes sense because in the real world, IS isn't a constant. Saturation currents or saturation current can change diode to diode, material to material, right? It's not one size fits all. So that's cool to see.
Yeah, I think it's just like, I guess, like experimental values to determine that IS.
It is the finagle factor.
There you go.
I still can't get that out of my head, dude. I'm terrified of the finagle factor. It keeps me up at night.
Like, yeah. Oh, no.
There's no response. It is a terrifying idea.
It is like one of those things. It's like I've legit had dreams where I'm in the middle of a test and I can't find like where did this variable, what is it?
It is the
finagle factor. Literally, I had to on a physics 2 lab. I had a variable that I could not for the life of me figure out, and it was due in an hour. And I literally just did some estimations of what the answer should be. I just started shoving in numbers that made sense for finagle factors. And that haunted me that I had to do that.
Finagle factor.
And it's like, I don't like just shoving random butt numbers in there with no
welcome to the real world.
Way. But hey, it worked. I got an A on it. So
here's how this works. Right? Here's a life lesson. Math does not fit the world. You make the world fit the math.
You're right.
All right. Your turn. Or anything we want to... Yeah, that's everything.
Yeah.
Dude, that's like nothing on
exactly.
Semiconductor diodes.
Yeah, so on what?
We need go over
this is barely
problems.
anything on diodes. Like I figured at least I didn't realize the test didn't have like I guarantee he's gonna give us one of the problems where you have 2 or 3 diodes in the
circuit. Yeah. I mean actually I feel like what'd you say?
Like the one where you have to do the truth table, figuring out like which ones are reverse and forward bias until your numbers.
You mean diode logic?
Sure.
He had
what he called it.
I saw that. I fundamentally despise that concept, but I understand its importance.
There is I know he does have
this.
Yeah, that guy.
Oh yeah, you're gonna have to swap all of them over. Wait, I haven't seen this. Where's this from?
He glazed over it in class.
This
one
right
day.
here.
Okay, I saw something like this, but oh golly, that's 3 diodes.
Yeah, so this.
He said he wouldn't have more than 3, or more than 2.
This, my friends, is the predecessor to our favorite TTL logic system, transistor logic, and it sucks. I hate diodes so much. I hate diode logic, I should say. You can see. This is ridiculous. That's all I really have to say about it.
I just keep seeing not plausible, and I'm like, yep.
He's basically talking about the only plausible state is 3 volts, 3 milliamps. So I guess this is to have the current you need on the output. So I don't even know what's happening here.
Well, it's because you have to do the equations where like, you're not going to have, oh, the current equals 5 here, but the same current equals 6 over here. That doesn't make sense. Was kind of the deal with it. Let's find an example that's not 3 of them. There are other tests. Oh, there we. Oh no, still. That frame rate dropped though.
Was that a frame drop?
Yeah, like we saw you go from like 7 to 5 or 4, like.
Yeah, I think that's the only one that he really went over in class.
I would suggest go to English's ones for diode deals, because those I remember they were plentiful, and they worked. It was good.
Nah.
I'm looking for where she had them. You might not have it opened up. I can't remember exactly where they are. Oh, and she has a practice test too.
Pog?
Oh, nice.
Yeah, module 4.
More practice.
It's practice problems.
Wait, found it.
You found
Wait,
it? There we go.
This is something different though. I don't know if this is, I don't actually, as far as I know, I don't even know if what he just showed was, it said state table. So I always think of it as diode logic, but I don't know if that's what he was actually doing there. It just looked it. Oh yeah. I see diode state. So it's, yeah. All right. So we have 5 volts coming in, 2 volts coming out D1. 40 kilo ohms on the output of D2, and we need to find Vx. Is that what it wants? Yes. And we need to find the current flowing into the system. So there's 4 combinations of on off. So you assume D1's on, D2's on for this portion, but you could also assume D1 off, D2 on, D2 off. Yeah, D2 off, D1 on, and both off and both on. So those are your 4 possible combinations for this. So this is, in this instance, powers of 2, my favorite, because it's still binary. This doesn't look too hard. His slides made it look a lot more complex than it needed to be, but he was also using 3. Someone said that he said he'd only do 2 diodes on an exam?
Yeah, he said specifically that he would only do 1 to 2.
Okay.
Just because for time reasons. And
Cool.
that in real life you would have computers and stuff to do like more than 3, so don't bother
I
with
thought
it.
he said he would give us up to 3, but no more than that, but I could be wrong.
All right. Well, I'm scared then.
Well, he has many an example of 3. I guess we'll look at this 2 first, because this one doesn't look too complex. So redraws 5 volts, because we have a 5 volt supply here. And
So
that means, what is that? I1, so that's diode, current for I1 must be greater than 0. Current for I2 must be greater than 0, because in this instance, she's assuming the state cycle of they're both on. So both of them require current in the branch. So fundamentally, the method you solve these problems, it looks like, is it's all about your assumption table, which is what he did for the 3s. She simply went right to the assume they're both on, because odds are assuming they're both on is probably the main solution, like the main line solution. But it's possible, depending on the circuit, the resistances, the voltages, that you could also have another combination that is feasible. So that's why you have to test all.
And I feel like the on position is the easiest place to start.
Well, that's what I said. So essentially what I meant with main line is odds are, like, all diodes in a system, if they're all on, the system's probably functioning. So it probably works. So it's a mainline solution. And then you have edge cases where it could be like, oh, well, you only need diode 3 on here because of the resistance is over there, consume all this current or something like that. So that's that. Cool. So looking through, if we're assuming that there's a current in this branch, and we have 2 volts at this node, why does she assume that? Is it because we have 2 volts here?
Yeah, it looks like
Yes, it is. They're in parallel, right? And she gave us 2 volts here. Therefore, this has to be 2 volts at this node, and there's a voltage across that. Boom, checkmate. Okay. Knowing that, we can calculate the current of IY, which is the branch current of the mainline supply over here, which is a voltage drop of 3 volts. Checkmate, easy. Because that's what she gave us with this data right here, the plus 2
And then
volts.
you can find I2 by just doing 2
Yep.
divided by 40k ohms. And
Yeah, and you can do I2, and then you can solve I1 through that, and you're checkmate. Okay, that's not bad. I can see. I think he's gonna give us a 3. That was too quick. That's too easy to do. He'll give us
I
a
was
3.
thinking he would give us a 2 that wasn't in parallel,
A
let me rephrase
series.
that. Yeah, no, I mean like, I'm trying to think. I just
I
different.
think if you
like more into the
swapped,
homework assignments.
I think if you swapped the values of those resistors,
Mhm.
like put the 40 where IY, the current going through IY, and then the 10 kilo ohm between D2 and ground, I think that situation you would have a different diode configuration, and one of them might have to be off.
Yeah, like if you instead of having ground, have a current there. I mean a voltage source there.
Yeah.
Well, yeah. So the reason this even functions, or the reason this is even a thing, is this wouldn't be a problem if she didn't give us that data point on D1 telling us the voltage out.
Mm-hmm.
So what you just said there by switching the resistances, like that's the whole fundamental trick of these problems, right? So if there's different resistances, then a certain branch might not need to be functional
Right.
in order for the system to operate. And that's why we have to test all those edge cases, because we don't know from the beginning if that's the case or not. So we have to test them.
Why
So
is there
these
not a
aren't that
voltage
bad.
drop across the diodes?
Traditionally, I think
are
you
you
would,
assuming ideal diodes?
yeah. So we would assume ideal diodes, and it says start by assuming diode states. So assuming ideal diodes, there's no voltage drop. If you think you have to assume a voltage drop, stick with 0.7 voltage drop per diode. So in this case, you would have a 0.7 voltage drop across D1. Therefore, the voltage drop across. Yeah, therefore that changes the answer, because then that means you received 2.7 volts across that I1 branch. Therefore, the voltage drop across the resistor isn't 3 volts. It is in
That
fact,
would be like
yeah,
have
it'd be 1 point or 2.3 or something. Wait.
Right, which then you'd have to subtract the 0.7.
Yeah, so it would change the
1.4
answer,
or
but
something.
I doubt we'd have to assume that, but if so, just know that all that would end up doing is changing your IY, your supply current.
Okay, I just was curious, like why we didn't even have to do that, because
Yeah. In most
yeah.
cases, just like op amps and stuff, we just get to assume a bunch of stuff to simplify things for us. Although in the diode case, I mean, I don't think it's that hard to just add in that 0.7 computation, but oh well. Because in real life, if you're expecting 2 volts out of something, 0.7 voltage drop across is a significant chunk. So
Yeah,
you really
because I would change VX to what, from 2 to 1.3?
Yeah, I drop VX hard.
Yeah.
So that's important. Like, in real life, sometimes the assumptions you make aren't valid, and they will ruin the thing you're trying to build.
On his notes, does he say when he goes through like the 3 diode problem, does he say like he assumes ideal diodes? Because that'd be good to know what he's taken into account on his version of this.
CPE.
I'm right now gonna look through some of his lecture notes to see if there's something that would be nice to pull up.
Definitely not this. Oh, right here it is, right here. Assume ideal diode model, right here.
Okay, so for this then we're basically just looking at short circuits and open circuits for everything.
This isn't an AND gate, is it? No. Is this even a gate? I don't even know.
Exactly.
I'm not paying attention. I could make literally, give me a transistor and I can make any combinational logic system. Like, I don't care, but I despise diode logic just because it's old. Although, what is it? Do we count transistors as analog or no?
I can't say.
I feel like the answer to that's no.
Not typically, I don't think.
Yeah,
I think they usually consider digital.
I know I've been I have an interest in machine learning and such, and I've seen that there's actually a push to go back to like I say go back, but I really mean advanced analog technology, particularly diode logic and analog computation, because analog systems are more ideal for machine learning applications than digital systems, or at least like some machine learning applications. And it's kind of ridiculous. Like return to the Stone Age in order to advance to the future. That's a weird idea, but it's interesting to say the least.
Well, we have some very basic technologies that if we advance better would be better overall.
I mean,
But-
analog is great.
Yeah, it can be.
Let's see.
It's just less error prone. It's more of a thing that if we were to build something while we're on Mars or on the moon or somewhere not on Earth, it makes a little more sense for the manufacturing.
Rest in peace, the analog circuit when I decided to shock it with my electrostatic discharge. Unfortunate day.
Do you want to keep looking at that? Maybe lecture 9?
His lecture 9?
Yes. Because he goes like and writes the step-by-steps for solving two diode situations. 1 second.
This is 4.3.
Scroll down some.
Yeah,
It should show it if you scroll down. Yeah, there we go.
This?
Yeah.
Yeah, that's
Just
way
more
neater
diodes.
than the last lecture.
Trial 2 or trial 3? These actually, I think these are all the same problem, aren't they?
Yeah, it's the same
Yep.
problem.
Starting
just
from
different
here,
trials.
4.3, and it's all, so this is 2 diodes, meaning he tested all 4 states. As opposed to
Yeah.
English, you simply went to the mainline state.
And was right somehow.
I that's what I'm saying. I feel like the mainline state is almost always like gonna be correct, but I
But
might
with
be
this one,
wrong.
it's not. But also,
Wild.
if you see here, it's because there's voltage sources on the other side of each diode,
Mhm.
and that kind of screws things up.
I don't know if it's voltage source is it the voltage source on the other side of each diode, or is that
Well, look how
function-
Reese draws.
Yeah.
how you're draw yeah.
They're not
I see it.
actually. He said functionally, like just redraw it like this, and you can just do this as a voltage source because that's what we're more comfortable with, and it's a little bit easier to deal with. Even though it's probably not that. It's just a potential difference.
It's just
meaning
that's the voltage you want out of that diode logically
Yeah,
for the logic to
but
function.
it's easier to work with when it's a nice little
Yeah.
rectangle.
Because functionally, you could actually probably augment this and do this and make this look real 223-esque and be like, and there you go. Now I
Hey,
understand
That's the ground node.
Yeah, I mean, the thing is, I see that, and that's how I draw stuff in multisim, and I mean, it works. Complex sources, you just slap a ground node in there, easy. But yeah, so that's that. I gotta delete that doodle.
Does Multisim have a Mac download?
I don't talk to
Or did I-
people with Macs, so.
Hey,
wouldn't
I
know.
got it given to me for free for Christmas. Okay, I can't help it.
Okay, fine.
when I have the
So-
money and this thing becomes slightly obsolete, I'll go to the ways.
You
it's
act as
supposed
if
to
it
be.
wasn't obsolete from the moment it was constructed. Either
Okay,
way.
for coding with C++, it's nice, but that's about it.
Sure, console yourself. All right, so we have step 1, where what did he assume here for starting? Oh, this is try 1, never mind. This is try 1. I
Yeah,
mean,
try.
his step 1 is redraw. His step 2 is develop a truth table with your diodes. What does this even mean? Oh, that's
Reverse
reverse
bias
bias,
and
forward
forward
bias. I
bias,
get it, yeah. I'm just gonna, if I ever do this, I'm just gonna replace it with on and off. Or hear me out here. I might have just had a breakthrough, a 1 and a 0. All right. We have 4 possible states here. Cool. Come over here. Pick a row in this thing, and does this stand for truth table by any chance?
Yes.
Oh
TT.
no. Yeah, TT row condition, and then use this stuff on your thing to, doodle oodle. So this is them both on, and it doesn't work. Cool. This is D1 is off, D2 is on.
Now
This
I kind
one
of
does
am
not work.
confused on how he does it when he turns them off, because for whatever reason, I'm trying to
He
look
draws
where it is.
what does he do?
It's just drawing
That's
an
a
open
short.
circuit.
I mean, an open
yeah,
circuit.
Or, yeah.
Yeah.
Well, not now in that part. I'm talking about in the KVL equation. I'm trying to look what I'm talking about.
So
Yeah,
let's
he
go
does VD1.
down.
So like right under his same note, I equals D2 for the trial state.
Yes.
You see the 3 minus 2KI plus VD1. I guess we're just going to do the voltage across the.
He's solving for VD1, it looks like.
Yeah, which I guess
And-
that makes sense.
And VD1 has to be a positive value.
But why? I guess because
it's because of the biasing, right?
is the bias. Okay, so if it was pointing the opposite direction, it would it be minus VD in the KVL equation? Is that KV? Yeah, KVL. Would it be minus VD or
I
did it
don't
still
know if
say
it's I
positive
don't know
VD?
if
It needs to be a negative value. I'm trying to think of
it
how
should still be. I don't know if I don't believe the sign of VD changes necessarily. I think what changes here is the result of the other terms has to be positive in order for it to be a
Okay.
plausible state.
So
Because
if this
think about-
bias was pointing the opposite direction, it would be fine.
If this was on, then yeah.
Mm-hmm.
So
Okay.
the reason is because this is reverse biased, right?
Yeah.
The only way this is reverse biased and functionally off is if the voltage is moving through it in the wrong direction.
Oh, okay. Yeah,
But the thing is, if the voltage is negative and it is reverse biased, that is a flip, and that would mean it's going the right way, and that's not right.
Yeah.
So what this is saying here is for trial 2, it's saying that that's forward biased, and it's not. So it has to correspond with your table,
Mm-hmm.
and it doesn't. And then here he
Okay.
turned off 2, and it worked because it's positive. So it fits with the logic of the table. It's all about
Okay.
it looks like everything here is ultimately based on the sign of your final answer, and that's
Mhm.
about it.
And that was the logic that he said that I was kind of confused me, but that makes a little more
Yeah,
sense
it's
now.
it's
kind
really
of
just
drew it, but-
referencing, based on
Yeah.
tables. Yeah, that's cool. I still despise diode logic, but I understand its importance. All right, that's that. Are there any other topics
I
or
wonder
things?
too, can you like think about it in terms of like high and low potential voltage between the points? So like
Yeah, you could think of it and you can write those potentials however you wish.
because I'm just thinking it's like, oh well, like there's the highest potential between like 3 volts and 1 volt versus 3 volts and 2 volts. So if one of those only one of those diodes is going to be on, it's going to be ID1, right?
ID1 is forward biased for the correct state here, yeah.
Right. I guess like I try and think about it in terms of just like on and off.
I mean, yeah, that's what as I said, I was like,
Yeah.
oh, maybe I'd replace the forward bias with on and reverse bias with off, or better yet, one is here.
Yeah.
I was essentially just memeing on the fact that this is just 202.
Yeah.
It's almost like digital logic applies equally to diode logic and transistor logic. Literally identical. The math is the same at the end of the day.
Almost took that course this semester.
202
and
digital
then-
logic,
Yeah,
fun stuff.
next semester though. I mean,
Fun
So-
stuff. You'll learn how to do math that isn't in base
Again?
10. Yeah, they'll just teach you math again. I think the best thing about math is the fact that the rules are the same regardless of the base. It's just we were taught the rules in base 10, so we have trouble figuring out that they're technically the same.
Yeah, I think that's when you realize it's like, oh, it's all literally just the same thing. And like
Yeah.
when you start thinking about base 10, like you would think about base 2 or something like that.
Yeah.
It makes things so much easier.
Yeah, it's almost like math is not like some hardline process that can only be done one way, and it's actually more of a logical system that can vary depending on what you're doing with it.
Hey, you should like, write that down or something.
Yeah, it's almost like
There's a book about it.
it's almost like there's like a guy who might have said that before. It's almost like math is logic or something. All right.
Jeez.
Either way, so I think that's everything that we
Have
have to
we
cover.
have we covered everything from the study guide? Like
Yeah, here, let's open her
section-wise?
up. I have it open here. I opened something else that you can't see, but I'm going to drag it into view. Here it is. Voltage, currents, rectifier operation, diode logic gates, and OR gates. We'll look and see if he has those, but I think he does. But we'll go back after this. Forward reverse breakdown regions. We have a decent understanding of that. That's something he said. Understand what nature gives you with temperature and semiconductor diodes. It ain't good. Pardon my bad luck. Hey. Know all models and especially the small signal model. What is meant by a small signal to a diode?
I think it's like less than a change of like 5 millivolts, right?
I suppose. These are all theoretical concepts, and I found, like, particularly in the last study guide, a lot of the theoretical concepts, like he says, like, this is like, if you don't know this, you might as well be dead or something. They don't actually come into play per se on exams for exam questions. It's just information that's fundamental to the understanding of the concept as a whole.
Yeah, or
So
if
it's still
it's
important.
in like a true false.
Yeah. So a lot of the stuff isn't as grade-wise, in order to do well in the class, isn't as important as one would like it to be. But at the same time, if you want to perform well as an electrical engineer or a CPE, or you're going to want to know these things so you don't get jumped and make a mistake. Because in the real world, you work almost exclusively with theory and rarely with actual stuff, sadly. Particularly for EEs, we are like the definition of theory engineers. What do we have? Read for your education. Nope. All right. Big time stuff here. Voltage regulation. That's what that whole design problem is for. And that's also what Zeners help us with. Full wave, half wave power supplies. So that's also, you know, applications of diodes and such. Another thing that design question helps with, particularly applications of full wave. Basic power supplies. Yeah, we know this yet again. So a lot of the stuff power supply wise is covered with that design question and is done, you know, out of the test time, and it's just done as a homework assignment. And there's a summary for 229 and 230. I feel like that's where he pulls his multiple choice questions from. I mean, his true false questions. I read this. I remember I read this. We don't need to read it again. So that's that. Maybe we could go back and look real quick if he has anything on the power supplies. This is the take-home problem. What does he have? Is there anything? Oh boy. Oh yeah, it's all sideways. This is RDL logic. This is the Zener, I think. Actually, wait, yeah, here's his power supply stuff. And his half wave, full wave.
I think he only really touched on in class, like ripple voltage was all he really talked about.
Which is something you need to know for that design question.
Yeah.
Oh yeah.
Okay, well, he talks about transformers here. All my homies love an iron core. All right, let's scroll on through. Does he talk about why iron cores are normally layers of metal as opposed to just a solid chunk? No. I feel like that has something to do with eddy current. I don't remember.
Anyway.
Let's scroll down to the supply stuff. The whole enchilada, you see.
Was that the RC transient stuff right above
Wait.
this?
Do you think the layers has to do with like thermal like coupling or like the changing of its size more?
I couldn't tell you. I feel like somewhere in my life I heard it had to do with eddy currents, but I really couldn't tell you.
Well, but wouldn't eddy currents cause the metal to heat up more, which could cause thermal expansion?
Probably.
And
So
also, I'm also, if you guys remember, charge primarily flows on the outside of things. And so what they might
more
do
surface
is have
area.
like a,
Well, is it? Here's the thing,
Exactly.
though. Here's the thing with
they might
regards to
do a core that's
transformers.
more
In a transformer, technically, charge doesn't flow across the core. It's a changing magnetic field through it, and the core
Oh, yeah.
focuses it around. Because you can have an insulated wire, and it's essentially induction, right? So it just goes brr.
That's an induced current.
Yeah, so like I have touched many an iron core of like an 120 volt wall supply in my life, and I didn't die instantly. So I'm pretty confident there isn't charge per se flowing, as opposed to a changing magnetic field that generates charge.
Well, there also might not have been a perfect potential difference between.
Yeah, me and
You
yeah, that's
and it.
fair. I should have licked it. Even
And
so,
we'll also held like natural ground at the same time.
yeah, smart play. I'll try that next. I have a transformer.
Yeah, but just make sure you hold one with one hand and the other with the other hand.
Pog. All right. So here's our full wave that Jacob didn't know that this resistor's not supposed to stay there like that.
Shut.
Yeah, that's just your load resistor.
Yeah,
right?
so that's just the load resistor, but he was
Okay,
asking.
you need to realize that that was 40 minutes of my life that I'm never going to get back. Going, what the crap do I do with this thing?
Yeah, let me just short my circuit across a load resistor as
It
opposed to
didn't
deliver
make sense.
to the
Okay,
circuit.
it didn't make sense.
Poggers. All right. So this is that. So here's your full wave, and then you'd be like, power here, and then you ground
Yeah,
it.
and then there's your filter coming
And
out.
then here's
of
the
that
filter
right
circuit.
next to
So
it.
here, yeah. So when he says the whole enchilada, this slide is how to do just how to do that question, and then you can just scroll past it.
Yeah, you basically just scroll back up real quick. Yeah, you basically just take the bridge rectifier, slap on that capacitor circuit, and then the shunt.
All my
regulator
homies love a
at the end.
capacitor circuit.
Now, okay, now with the resistor, we only really need 2 resistors with this, I'm pretty sure. Like you
Yeah.
just
So when you do your
like, you don't-
math, if you get a
Mhm.
resistor value that you need, that's like stupid weird, then obviously you'll need more. But
yeah.
in real life, you could theoretically have like a tailored resistor, and you'd only need 2. You need the load
Yeah.
resistor he requests, and then you
And
need
then the one with the shunt.
yeah, and then you need your shunt thing for your filter. Right?
Technically, you could have one to make sure that the capacitor doesn't burn out, but we're not putting that much
Yeah,
current through it.
nah,
So
capacitors are fine, dude. I have 500 farad capacitors. I don't care.
yeah, they'll be fine.
Yeah, I only use 2 resistors for mine.
Yeah, it's pretty,
Yeah.
and one of them
I
was
played with-
required by the question. So
Right.
Yeah. So really, you just need the shunt. You're just you're just shoving all the figures together and then finding numbers for them.
magic. Yeah. So it's almost like this this supply may or may not be like,
That.
huh. All right. Yeah. So full wave is talking about how, hey, you see how a half wave only gives you these little jumps. The full wave be like invert. Pog, yeah. And then you're like, wait a second, but then wouldn't
No,
the
it's
full
fine.
wave just look like this? And then you're like, wait a second, what if I put a filter on it? And then it goes like, it's a little better. And then you're like, what if I put a voltage regulator on it? And then you're like, oh, what's a voltage
And-
regulator? What could a voltage regulator possibly be? And then you
I think it regulates the voltage.
yeah, and then you're like, wait a second. I feel like it starts with the letter of the alphabet. That may or may not be the last letter of the alphabet. Is it a Zener die? And then you're done. Yeah, that last figure that isn't as apparent is right up here.
I literally
Yeah.
drew up the entire circuit and
Oh.
then just like erase and drew the stupid rectifier.
Until you finally got rid of your
over.
load resistor. 'Cause you're
And then you're like, no, that's the load resistor. You don't have to have that stupid thing in the middle. I'm like, oh,
Pog.
Pocket.
Pog.
I erased the whole thing. It's all small. I'm gonna have to get a new piece of paper for it, but that's
Yeah.
okay. This was my first draft.
I wonder what happens if I use a voltage regulator MOSFET and just attach it to wall voltage. I wonder what happens. So this is him just talking about ripple voltage here, which is given by some equation. This is stuff that the students have to do on their own, so we can't discuss it in too much detail.
Understandable.
Computing filter capacitor. I mean, this is his notes, so if you want to know how to do those problems effectively, here's your reference material, gamers. And then this is talking. So okay, so we have that down. Diode logic is like over here. So I'm gonna scroll down and be like, flip, nope, flip, nope, flip. There we go. And here's our OR gate, and here's our AND gate. So remember how those exist and how they look like. Can anyone tell me how to build an AND gate out of transistors?
They're just in series.
Hell yeah, homie knows his AND gates. Can anyone tell me how to build a NAND gate?
Please stop.
Well, it's
Well-
just that's where you pull your power from.
Oh, okay.
So
can you just use like P or N channel ones?
oh, I don't care too much for the actual. I just use like a 2222 transistor, like power amplifier ones. This is what my this has nothing to do with this class, but we're drawn towards the end, so I'm just gonna be like this. So look at that. Look at that. That's nuts. And normally there's some resistance here that makes this like low current. You have, and then this is ground. And then here's your, your power, whatever that is. And then here's your controls. So for an AND gate, you pull your power signal here. So this is your output data signal. So that means in order for this to work properly, power needs to go through both transistors, right?
Yeah.
Now, you would think originally starting with transistors, be like, and logic in general, you're like, oh, well, ones and zeros, right? So, when I use a transistor, if I turn, you run into a problem here. You think, oh, well, when this system's off, when they're not both on, the output is going to be 0 volts. No, it's not. Turns out, even if there's no voltage that is being pumped through the, what is that? That's the, how did I forget the name of these connections? It's the collector, yes. Pump it into the collector. Here's your emitter. So you pump it into the collector. If there's nothing on here and you turn on the switch here, that little amount of current flows through. And that's a problem. So in real life, we have high voltage, we have high logic and low logic, but it's not 0 volts for our logic low. It's actually like half a volt or 1 volt or something. It took me a while to figure that one out. Either way, we're both on, voltage flows and you're good. Now for a NAND gate, you simply pull the voltage from up here instead. When they're both on, it bypasses the circuit and jumps to ground, thereby creating logical NAND. NAND and NOR are my favorite gates because they're called universal gates. You can make any combinational system out of those gates and never use another gate in your life. They're great.
Is it efficient though?
No.
It is cheaper though.
It is cheaper.
Oh.
And that's why they do it.
Yeah, that's like
There we
NAND
go.
flash and memory like that. Yeah, it's pretty great. But maybe one day I'll show you guys the. I have a system built of 8 breadboards worth of transistors assembled in NAND logic configurations that I use to make a random access memory unit. It can store 4 bits. You're welcome.
That's pretty impressive.
Oh, I don't know what to respond.
I'm impressed with
It can
that.
store 4 bits of data, gamers. That's 4, count them, 4 whole bits.
Now, are
Dude,
you just
that's
creating
a
like flip
piece of
flops to
paper.
store the bits, or do you have like actual?
They are D latches. So yes.
So, but like, do you have an addressing module to like address them and retrieve the bits?
I drew up a design for that and never built it.
Okay, no, that's fine. Like,
So
it's
it
still
is
super-
the only way to clock data in is to manually input logic highs during the on cycle.
Okay, but
as of
just
now.
you made like 4 D latches altogether to store the 4 bits.
Oh wait, no, I said that wrong. It's 4 bytes.
Oh,
D
4
latches don't
bytes.
take D latches don't take that much to bake. They don't
Well,
take
yeah,
that much space.
D latches there you get like I think 2.
You need 4
uh,
gates. 4 gates, which can be functionally, each gate can be composed of 2 to 3 transistors depending on the gate
Isn't it just
variety.
2 NAND gates?
D-latch is a little
Which
more
would be 4
complicated because
transistors.
I specifically use the gated D-latch, which looks like so. I am still writing, that won't work.
Okay, yeah, you got 4 gates. You got 4 NANDs
What?
is one way to do it.
Yes, this is the one I use specifically. Now, here's the thing. You see that problem?
Yep.
That's dumb. That's for idiots, right? So I don't use inverters because they're cringe. What the hell is this? What are they?
Those are D latches, man.
That's the wrong type of
Those
latch.
are like
It's a gate
those are
latch.
like actual latches. Those
So-
aren't logic gate latches. They're just
So
latches.
this one looks stupid because that's an extra gate, right? So in order to make an inverter, you simply tie these two together on a NAND gate, and then that's an inverter, right? But I don't want to use 5 gates. I only want to use 4 gates per latch. So instead, you do this pog move, and you'd be like, hey, did you know that this output is going to be the opposite of this output? Or this output's going to be opposite of the input? Pog.
Okay. Nice.
And then you save on a gate. And that's that. All right. Well, we're basically done. We're talking about latches now. That's useless for these people. I should say this class more accurately.
These people. Like
Yeah,
you're
well,
not one of us.
We're not people.
We're
we don't count.
engineers.
Yeah, we don't count.
We just contribute to the economy.
That is our purpose. Oh no, you can see my Steam notifications. My
Oh,
life
no,
is
someone's
over.
playing Rust. Oh no.
I love Rust. All right, I'm gonna stop recording now. Well, stop share, and then recording's over. Good luck, gamers.